presentation really quick. Okay. Good afternoon, everyone. My name is Sean Loesch, and I'm pleased to present for the 12th International Conference on Software Engineering and Applications in Toronto, Canada. I'm a senior undergraduate researcher and teaching assistant at the University of Wisconsin-Eau and am currently working under the supervision of Dr. Mounika Vanamala. My talk today will be about my debut paper, using machine learning to identify weaknesses from software requirement specifications. So to begin, secure software engineering is essential to contemporary infrastructure. Most of the luxuries and efficiency of the modern world can be attributed to the safe construction and operation of software and code. Society, as we know it today, would fail without software. There are over 20 billion Internet of Things devices, or devices that can transmit data over the internet, as of 2019. Such a precedent requires the software utilized by the masses to be secure, and a response was needed. Thus, the secure development lifecycle was born. The secure development lifecycle, or SDL, is the process in the software development lifecycle, or SDLC, in which security artifacts are prioritized first. This model is paramount in building safe and secure software. However, as with any precautionary measures, security is purchased at the price of time and labor. Such an observation is as old as software development itself. Even a former member of tech giant Microsoft's central security team acknowledged that reviewing thousands of files can be slow and tedious. So the question we wanted to address here was, is there a way to assuage this cumbersome, albeit necessary, effect on software development without harming the security of the end product? By looking through some similar literature, which I will soon discuss in a literature review, we came up with our idea. Since a considerable amount of time in the secure development lifecycle is spent identifying and correcting for weaknesses in the program or programs, introducing automation into the mix would reduce time costs. Additionally, if this problem was tackled as early as possible, time costs would, in theory, be reduced even further. We chose to work on automating the detection of software weaknesses using software requirement specifications, a crucial part of the first step in the software development lifecycle. To do this, we had to find repositories for examples of software requirement specifications and common software weaknesses. For software requirement specifications, we used the promise_exp, standing for promise expanded dataset, an expanded version of the promise dataset by Marcia Lima. The promise dataset includes a large preponderance of software requirements from a myriad of verified sources and was exactly what we needed. For the common software weaknesses, we used MITRE's Common Weakness Enumeration, or CWE for short, a community-developed list of common software and hardware weakness types that have security ramifications. The unique contribution of this work lies in the mapping techniques and algorithms we used, which I will cover in the methodology section. Now that I've developed all the pertinent information, I will cover the precedents made by previous research that affected our work. So, for the literature review, the first paper I will cover is Recommending Attack Patterns for Software Requirements document, one of Dr. Vanamala's previous works. In this work, the identification of keywords in MITRE's Common Attack Pattern Enumeration and Classification, or CAPEC, dataset was used to assist in recommending attack patterns based on software requirement specifications. To achieve this goal, the authors used a latent Dirichlet allocation, or LDA algorithm for topic modeling to test how accurate their ideas of topic modeling were in identifying keywords between CAPEC and software requirement specification documents. While going through this process, they also used a metric process called cosine similarity, which bases its math on how similar documents are, while not taking their sizes into account, and then creates two vectors based on each document and projects it onto a multi-dimensional space. However, this methodology is stated to be heavily dependent on the text describing the system due to it looking for specific keywords. Once the algorithm was run for topic modeling, it was found to be a success in identifying relationships between KPEG attacks as well as patterns from SRS documents. So a second paper that influenced our work is analyzing CVE database using unsupervised topic modeling, which is also one of Dr. Vanamala's previous works. In this paper, topic modeling and the LDA algorithm were employed to unveil themes within MITRE's common vulnerabilities and exposures, or CVE, dataset and align them with the Open Worldwide Application Security Project, or OWASP, top 10 risks. To achieve this alignment using LDA, the study underwent several stages, including data pre-processing, text cleaning, bigram and trigram modeling, constructing the topic model, visualizing topics and their associated keywords, and ultimately correlating these topics with the OWASP top 10 list. After completing this process, they identified emerging trends in cyber attacks. The analysis spanned 5-year intervals, starting from 1999 and extending to 2019. Remarkably, the findings revealed a significant resemblance between the recommendations in the OWASP top 10 and the increasing vulnerabilities reported in the CVE database. This congruence demonstrated the effectiveness of the study's approach and its ability to identify cybersecurity trends based on the striking similarities observed between the OWASP top 10 and the escalating reports within the CVE database. The third and last paper I will be discussing that influenced our work is Systematic Comparison of Vectorization Methods in Classification Context by Kirshashewska et al. In this work, using a continuous bag of words in skipgram, they obtained classification and keywords from a text document comprised of other pseudo-random text documents selected by the researchers. From there, they were able to take the information and create a summary statistic based on categories they wanted to separate these topics into by using k-nearest neighbors and naive Bayes algorithms to classify the information. Once they compiled the data, they found it was considered reliable. They found that even with a large data set, that there was no negative impact on the vectorization methods used to find these conclusive results. So based on this information, they found that there was a good relationship between the vectorization methods and the classification performance. While we conducted our research, we used techniques from this paper by matching IDs between the promise_exp dataset and the CWE dataset with help from the bag of words vectorization model. So getting into the methodology section here, before we could start training our algorithms, we needed to make our training set, meaning we would have to create a mapped relation between the promise_exp and CWE datasets. The mapping was 2 stages long, and in the first stage, we took a roughly 900-line text file from the promise_exp dataset with each line containing a textual description of a software requirement. For the CWE dataset, we simply downloaded their .csv file on their website and extracted each unique CWE ID and its corresponding description. To actually map them together, we first performed latent semantic analysis, or LSA, on each text file individually, creating keywords for each line and then using a support vector machine algorithm to create a map between the 2 datasets with a minimal amount of manual mapping in between. The vectorization technique employed for constructing our LSA, as I mentioned before, was the bag of words model, which is commonly used for object categorization representation, where key objects or words are selected from a larger parent object or a line in a text file in our case to effectively represent the larger object to provide some background. So in the second stage of the mapping, we abstracted the mapping to make it so that the lines of the promise_exp text file were mapped to the 40 general CWE categories, since we found it unlikely that the algorithm would be able to predict an extremely niched particular software weakness, but would instead be able to more accurately predict more general categories, such as privilege issues or documentation issues, to name a couple. This stage of the mapping was a bit harder since the more general categories weren't present in any downloadable version of the dataset. We had to use web scraping with the beautiful soup library in Python, as well as a very small script to transform each CWE ID to their corresponding category in the mapping. So once we had a complete CSV file that included each promise_exp software requirement, its mapped CWE vulnerability description, and the corresponding CWE category, we were then ready to test machine learning algorithms. These algorithms utilize the training set to predict and identify software weaknesses categories from software requirement specifications. When testing and training the algorithms, we used 3 different splits. The first was an 80-20 training test split, and then a 70-30 split, and finally a 60-40 split. So getting into the results and discussion, I'll first cover the algorithms that were tested. So in total, we tested naive Bayes, SVM, decision trees, neural network, and the convolutional neural network. And among these algorithms, the ones that provided reliable results were the SVM and the neural network. So I'll cover those first. So the SVM algorithm yielded an average accuracy of about 0.642, and to be precise, for the 80-20, 70-30, and 60-40 training test splits, accuracies of 0.648, 0.643, and 0.636 were obtained respectively. This moderate accuracy rate makes the SVM algorithm a clear candidate for further use. The neural network never yielded an accuracy below 0.86 after dozens of repetitions, with most runs ending with an accuracy higher than 0.9 and achieving a high of 0.992. The neural network had a batch size of 32 samples and went through 10 epochs before reaching its final accuracy for any run. After seeing these results, we concluded that the neural network is currently the optimal algorithm for use. So although the success of the results garnered from the algorithms mentioned previously is significant, it is essential to make note of the machine learning algorithms that did not work with the CWE and promise_exp mapped training dataset. The algorithms that did not work were naive Bayes and decision trees. At the time of the paper's acceptance, the convolutional neural network, or CNN, hadn't been developed enough to be able to conclude anything regarding its reliability, so I will not cover it during today's talk. I will now cover why the naive Bayes and decision trees algorithms did not work. So naive Bayes is split generally into 3 variants, which is Gaussian naive Bayes, multinomial naive Bayes, and Bernoulli naive Bayes. Only the Gaussian naive Bayes and multinomial naive Bayes were tested, since the Bernoulli variant deals with data with binary features, meaning each feature can only take on 2 values, which was not reflected in our dataset. It was not possible to have that reflected in our dataset. The attempt to use the multinomial variant resulted in errors due to the dataset not being able to assume the correct format for the variant to function properly. This is because multinomial naive Bayes expects data in the form of counts, where each feature represents the frequency of occurrence of a particular term or word in a document or sample. The type of data collection used for creating the training set could not include allocating data in this way, rendering the multinomial variant unusable. As for the Gaussian variant, results showed a low average accuracy of about 0.12 over the results from 80-20, 70-30, and 60-40 data splits. And this was most likely because The Gaussian variant works best with normally distributed data. And the features of our training data set were not at all normally distributed, which was the most likely culprit for its bad results. Thus, since the Gaussian and multinomial variants were thrown out and the Bernoulli variant was not applicable in the first place, naive Bayes was thrown out in its entirety. And the way the dataset was structured was the reason the decision trees algorithm didn't work as well, because decision trees rely on identifying patterns and relationships in the data to make accurate predictions. And since the value of our target variable in every row was unique, which was the CWID to be particular, there were no repeating patterns within the dataset for the algorithm to discern, yielding a low accuracy of about 0.1. So to summarize, in this work, we used the results from applying latent semantic analysis to the content stored in the common weakness enumeration and the promise EXP repositories, to map the best fitting CWE weakness category to each line of the promise_EXP dataset. The result of this mapping became the dataset that would be used in our experiments, as I previously explained. And this training set was created to allow us to build an algorithm that would predict the potential development of software weaknesses. Upon its completion, this algorithm could, in theory, be fed software requirement specifications and accurately predict which weaknesses would occur in the future so that secure software developers could expedite creating software in a secure manner with the same level of efficacy. We conducted an experiment to compare the performance or accuracy or precision of various supervised machine learning algorithms to arrive at the most optimal algorithm for the task. And we found that a neural network with 10 epochs and a batch size of 32 showed the best results in precision, troughing at no less than an accuracy value of 0.86 and peaking at 0.992 while remaining above 0.9 on average. So harking back to the beginning of this talk, secure software engineering is an onerous process. Identification of potential software weaknesses from requirements, elicitations, or specifications using an accurate machine learning algorithm would save developers a significant amount of labor and time in finding weaknesses in their code, and thus allow software of the same quality as before the existence of such an algorithm to be produced at an accelerated rate. We hope this study will help developers who want to optimize the secure development of software and produce high quality work at a faster rate. The training dataset developed could also serve as a reference for other studies, allowing other researchers to draw their own unique and useful conclusions regarding the optimal algorithm for use. And for future work, sorry, I kind of got to this slide a little late. I'm sorry about that. For future work, we intend to optimize currently working algorithms to provide new results with higher accuracy rates, test new algorithms in the search to find the optimal algorithm to use for this task, and correct the training set for error and optimize it. That was the end of my talk. Here's my contact information. I appreciate you all taking the time to let me speak today. It's been a genuine pleasure. If you have any questions, I'll try to answer them to the best of my ability.